So, good afternoon, students. Today we will start the topic that is the standard signals. And in the signal and a system subject, we are having a deal with the number of the standard signals. Means when we are solving the numericals of the uh, types of signals, or when we discuss the uh, numericals of the system. Okay, then we will uh, use these standard signals. Okay, so these are the very important from the like from the numerical point of view. And first of all, I will give you the brief about these standard signals. Okay, what are these types of the standard signals and how they are used in the different numericals. Okay, so one by one we will study these standard signal. Actually, we are having like a 7 types of standard signals in the signal and system. Okay, so one by one we will discuss each uh, standard signal. So first type of the standard signal is the unit step signal. Okay, so first type of the standard signal, that is the unit step signal. This is the very important signal, the important type of the standard signal. It is mostly used in the numerical part, and this unit step signal is denoted by the UN. Okay, mathematically it is represented by the UN. Okay, and when we are discussing this standard signal, when I am explaining this standard signal, first means I am explaining the unit step signal. So I will explain you the both the type. First, I will explain the discrete type of unit step signal. Then I will explain the time representation of the unit step signal. We will discuss both the type. Means first we will discuss the discrete type, then we will discuss the time, that is the continuous type. Okay, that is in the time domain, or that we will say that that is the continuous type. Okay, continuous type or discrete type, both. So uh, each standard signal is subcategorized into the discrete type or the continuous type. Okay, so this, when I am using the term n to represent the time, okay, that type signal is called the discrete type signal. When I am using the time t, okay, time is represented by the t, then that type is called the continuous type. And each standard signal is divided into the two parts. Means it is having their discrete type also, it is having their continuous type also. So each signal I am explaining, I will explain the both the types. Means first I will explain the discrete type, then I will explain the time domain continuous type, that is. Okay, so in discrete type, time is represented by the n, and in the continuous type, time is represented by the small t. Okay, so this is the like a unit step signal is represented by the, firstly I will explain you in the discrete type, that is the un. Okay, so unit step signal is the represented by the un, and this is the discrete type. Okay, means this is the discrete type representation of the unit step signal. Okay, discrete type representation of the unit step signal is un, and it is values 1 for n greater than or equal to 0 and 0 otherwise. So this is the un. Okay, un is value is 1 for positive values of n. We can say that the un, we can also explain it as the un is 1 for positive, means we are using the word positive values of n. Okay, so for positive values of n, un value is the 1. So we can represent this signal graphically as the, like this is the signal, this is the, we are having a like a un. Okay, this is the n. Basically in the discrete type, this x-axis we are represented by the n, small n. Okay, so it is value here, it is the 1. Okay, here value is the 1, here amplitude is the 1, means 0. This is the n is equal to, for the 0 value is the 1, for 1, 2, 3, up to so on, up to infinity. Okay, this value is the 1. This is the mathematical graphical representation of the unit step signal. Okay, so this is un value is the 1 for positive values of n, means for the negative values of n, means here we are, if I am representing this axis as the like minus n, this is the minus 1, its value here it is the 0. For the minus 2 value is the 0. Okay, so its value is the 0 for negative, I am saying negative values of n. Okay, so this is the un, basically unit step signal, and we are using these signals very much in the like a numerical part of the signal and system. Okay, so this is basically un in the discrete time. I will explain you unit step signal in the time domain. Okay, so this is the un unit step signal representation in the like for the discrete time signal. Next, I will explain you un for the like here I will explain you that is the ut. This is in the continuous time signal. Continuous time signal. Okay, it is in represented a continuous time signal. This is the ut, small t basically, and this value is equal to the 1 for t greater than or equal to 0 or 0 otherwise. Okay, this is the unit step signal. Unit step signal is the in the continuous time signal. Here we are replacing simple n by small t. Its value is the 1 for t greater than or equal to 0 or 0 otherwise. So how to represent this signal? We are like a draw the x-axis. Here it is the t, and here we are having a minus t. Okay, so its value is the like this one. It is representation is like this is the ut, and amplitude is the 1 for the t is greater than equal to 0 or 0 otherwise. So this is the ut representation for the time domain, continuous time signal. This is continuous time signal, this is the discrete time signal. So this is the first signal, that is the unit step signal. Basically this is the mostly used standard type signal. Mostly the numerical came like in which we are using the unit step signal. Like in the previous lecture we have done the numerical of the power signal and the energy signal. In that we are also using the same standard signal. Find out un is the power signal or the energy signal. Okay, so we are using this type of signal in every numericals, like a type of signals, whether the signal is the energy signal or the power signal. So this is basically a first type of standard signal. Next, I am rubbing this first signal, that is the unit step signal. Second type of signal we are having, that is the standard signal, that is the signum function. Okay, second type of the standard signal we are having, that is the signum function. So signum function is like we can represent, this is the new type of signal function. Basically mostly examiner ask these questions on the what is the signum function and how it is represented. So signum function, first I will explain you in the continuous type. Okay, so signum function is denoted by the term SGNT. Signum function is denoted by the SGN word, that is the SGNT. and it is represented by the, like its value is the 1 for t greater than 0, and the its value is the -1 for t lesser than 0. Okay, so signum function is having the value 1, okay, for t greater than 0, means when your time is greater than 0 for positive values of n, for positive values of t, sorry. Okay, so it is graphical representation of this signal is like, here we are having a t, here we are having a minus t. So a signum function is represented by, for positive, here we are having a 0 for positive values of t, means 1 2 3, its value is the, its magnitude is the 1. Okay, this is the signum t function. And for the negative values of the t, its value is the -1. It's is for the negative values like -1 -2, this is having the value -1. So this is the signum function. Similarly, for the discrete type of the signum function, like it is denoted by the SGAN, and it is represented by this signal by the, here we are taking the positive values of n, here we are having the negative values of n. So it is represented by the SGN function, and it's for the positive values of n, like for the 0, here we are having a 0. Okay, it is value is the like a 1, it's 1, it's 0 1 2, magnitude is the 1 1 1. Okay, up to so on. For the like a negative values, it is the -1. Okay, this is the -1, this is the +1. So -1 -2 -3 up to so on, we are having a -1 magnitude. Here we are having a +1 magnitude for the positive values of n. Here x-axis is the n in the case of the signum n function. So this is the second type, that is the signum function. Okay, so third type we are having a, like a third standard signal we are using, that is the rectangular function. It is also important functions, that is the standard signal. Third type of the third type of standard signal, that is the rectangular function. So it is called the rectangular function. So a rectangular function is, its shape is like a rectangular pulse. So it is represented like a, for the time domain signal, it is the, like if here we are having a time t, it is the negative t. So if I am taking the pulse of amplitude 1, okay, this is my RECT rectangular function. This is in the continuous time signal t. So its magnitude is represented by the 1. Okay, so here we are having a -t, here we are having a t function. So it is the rectangular t, and its magnitude is the 1. Okay, so here we are taking the x-axis, we are representing the timeline. It is the -1/2, and it is the 1/2. Okay, and between this time range from the -1/2 to t 1/2, its magnitude is the 1. And how to represent this equation in the terms of the mathematical, that is the, it is represented by the RECT rectangular t, and this is equal to the, its value is the 1 for t, like range is from the t, from the, we can say that the -1/2 to t 1/2. Okay, for this range of t from the -1/2 to 1/2, its value is the 1, and its value is the 0 for otherwise. So this is the rectangular function, and mostly we are using this function to solve the numerical parts of the type of signals or the type of systems we are using here. Okay, So we can also for the standard rectangular signal, okay, for the standard rectangular function, we are representing it by the xt function, that is equal to the a rectangular, that is the t by capital T. Okay. So what is this? This is the standard equation. This is the actually a standard equation of the rectangular function. Okay. So it is the xt. Xt is the function. What is the a is showing? A is showing the amplitude. Okay. This a is showing the amplitude of this rectangular function. Here the amplitude is the one. Okay. That's why we are using the one. But here a is representing, that is the amplitude of this rectangular pulse. Okay, so this is the amplitude, and here capital T, this capital T, and here we are having a small t. So this small t is representing the time. Okay, this small t is representing the time, and capital T is representing the width of pulse. Okay, this capital T is representing, that is the width of the t. In this case, this is the width of the pulse. Okay, so what is this function in this case? So if I am drawing the like one rectangular pulse, this is the time t. Okay, so this is the re function by xt. Okay, this is the my function xt. I am denoting here function xt. Okay, this is the x-axis is representing time t minus t, and I am drawing this rectangular pulse. Okay, this is the rectangular pulse, and the amplitude of this rectangular pulse is the A, capital A. This A is representing the amplitude of this rectangular pulse. And the width of this like a rectangular pulse, it is the capital T. So this is actually the rectangular function we are having. This is represented by this equation. Xt is equal to A rectangular. A is the amplitude, rectangular, T is the time, and capital T is the width of the pulse. Okay, so this width of the pulse is the capital T. Okay, so uh, this is the rectangular function, and we can use this rectangular function in the discrete time also. This is the representation of the rectangular function in the time domain basically. Okay, this I have explained the rectangular function in the time domain. We have taken the xt as the function, a as the amplitude, and here t, small t, is representing the x-axis. We are taken the x-axis as the t. So here we are representing the t, and this capital T is representing, capital T is representing the width of the pulse. What is the width of the pulse? That is represented by the capital T. So this is the basic rectangular function that we are using in the signal and system. Next type of important function we are having, that is the delta function. This is all about the rectangular function. So next type of important function, standard function we are using, that is the rectangular function. After the rectangular function, we are having the next important type of the standard signal, that is the we are having a delta function. Okay, that is the delta function. Delta function is also called as the unit impulse function. Okay, this is also called as the unit impulse function. Okay, this is the very like a important function, important standard signal function, means like a unit step signal. Then after a unit step signal, we are having a unit impulse function, then unit ramp signal. These three signals, like a unit step signal, that is the like a we are represented by the un. This is the important. Second one, this is the delta function, is also important. Third one, we are having a unit ramp signal, that is the UR, that is represented by this type of signal, UR representation. These three signals, first, second one, third one, these are the very important signal from the important standard signals in terms of signal and systems. Okay, so we are maximum use these three signals in the signal and system. Means in every chapter, like a Fourier series or in the LTI system, we are maximum using this unit step signal, unit ramp signal, or the unit impulse signal, impulse function signals. So coming toward the second type, that is the like we are having, that is the delta function or the unit impulse function. So delta function or the unit impulse function, firstly I am talking about the continuous type. Okay, so in the case of the continuous type, like in continuous type we are representing the signal by the t, it is in the time domain, so it is represented by the delta t. Okay, so delta function is represented by the delta t. And what is this delta t? Delta t function is having value 1. Okay, its value is the 1 for t is equal to 0. Okay, means when your time is 0, your delta t function value is the 1. Okay, and its value is the 0 at the otherwise. Okay, means at the other positions its value is the 0. This is the delta t function, and its value is the 1 for t is equal to 0 or 0 for the otherwise. If I am drawing this delta t function, means this is the t, and here we are representing the minus t. Okay, so this is the like a function, that is the delta t. Its amplitude is the 1 for t is equal to 0. Okay, rest at the all the positions like 1, -1, its value is the 2, its value is the 0. Means its value is the 1 at and t is equal to 0. This is called the delta function or the unit impulse function. Okay, they are having only a single value at the t is equal to 0, amplitude is the 1. Okay, rest at all the other positions the value is the 0 basically. Okay, so this is in the continuous type. Next is for the discrete type. Okay, for the discrete type we can represent it by delta n. Okay, here we are representing the uh, time by the n. Okay, in the continuous type, again I am repeating, time is represented by the t, and in the discrete type time is represented by the n. So its value is the 1. Okay, its value is the 1 for n is equal to 0. Okay, at means its value is the 1 for n is equal to 0. Okay, means for n is equal to 1 its value is the 1, and for the other positions its value is the 0. So delta n is represented, here we are representing the n, here we are representing the minus n. This is the delta n value, its magnitude is the 1 for n is equal to 0. Okay, means at n is equal to 0 we are having the value is the 1. Okay, means at n is equal to 0 its magnitude is the 1. Rest at all the other position, n is equal to 1, n is equal to 2, n is equal to -1, n is equal to -2, its value is the 0. Okay, at the other position its value is the 0, and its value is the 1 for n is equal to 0 or 0 for otherwise. So this is the delta function or the unit impulse function. Okay, basically this delta function or the unit impulse function it is using in the shifting property, means like in the linear time invariant system, when we are having to find out the value of the signal at particular point, okay, then we are using this delta function. Means I am giving you the one example. Suppose I am having this continuous type of signal, okay. So continuous type of signal I am having like a t, and this is the xt is the signal. If I want to find out the value of this signal at particular time, means at t is equal to 0, what is the value of the xt? So what I will do, I will do multiplication of the xt with the delta t function. By using this multiplication, I will find out the value at the t is equal to 0. Okay. Next, second part, what we will do, we will shift this signal. Okay, we are shifting this delta t signal either toward the right side or either toward the left side. That is related with the time advance operation or the time delay operation. When we are using the time advance operation or when we are using the time delay operation, we are shifting this signal toward the right side or toward the left side. Then by shifting this signal toward the right side or toward the left side, we will find out the value of this signal xt at any position. Means suppose I want to find out the value at the t is equal to 2. Okay. So I will shift this signal toward the 2 step toward the right. Okay. Then it is having the value 1 at t is equal to 2. Okay. Then we will multiplying this signal with the this. Then we will find out the value of the xt at the time is equal to 2 seconds. Okay. That is called the delta function or the unit impulse function. Okay. So later on we will discuss this in the detail how we are using the shifting properties to find out the value of the signal at the particular instant of the time. Okay. So this is about the delta function. Delta function is what it is also called as the unit impulse function. Delta t, it is represented by the delta t in the continuous type. Its value is 1 for t is equal to 0. Okay. Means at only single point t is equal to 0, its value is the 1 or its value is the 0 or otherwise. Okay. Similarly, in discrete type, it is represented by the delta n. Okay. And its value is the 1 for n is equal to 0. Rest its value is the 0 for the other positions. Okay. So this is the delta function we are using in the numericals of the signal and system. Next type we are having, that is the unit ramp signal. Third, like our fourth type we are having, that is the unit ramp signal. Next, like a type is the unit ramp signal. Okay, its shape is like the ramp we are having. Okay, so this unit ramp signal is denoted by the U, R, and type. R is here representing the unit ramp signal. Okay, so its value is the n for n is greater than or equal to 0 or a 0 otherwise. Okay, so this is the U R N. Its value is the n for n greater than or equal to 0 or 0 for the otherwise. So how to represent this unit ramp signal graphically? Okay, so first of all we will take this x-axis as the n and this is the minus n. Okay, So its value is the n for n greater than or equal to 0. Means we will find out the values of unit ramp signal for the positive values of n. Okay, so we are talking about the 0, we are talking about the 1, 2, 3 positive values of n. N is greater than or equal to 0. Okay, so at the n is equal to 0. Okay, at a value n is equal to 0, its value is the 0. Means for the n is equal to 0, its magnitude is the 0. URN value is the, we will write, I am writing here. Here I am writing the like n. Here I will write down the URN. Now I will take n greater than or equal to 0, its value is 0. URN is the 0. If I am taking n is equal to 1, its value is the URN value is also the 1. Okay. If I am taking n is equal to 2, URN value is the 2. So it is whatever I am taking n, URN value is same. Okay, that is the unit ramp signal. Okay, so here I am taking n, so URN value is the 0. At 0, URN value is the 0. Now I am taking n is equal to 1. This is the n. I am taking n is equal to 1. What is the URN value? It is again the 1. So I am drawing the magnitude here. It is the 1. Now I am taking n is equal to 2. So what is the value of the URN? It is again the 2. So it is the, I am drawing here, it's 2. For the 3, I am taking the value of n is equal to 3. It is the 3. For the values of the 4, I am drawing here, it is the value is the 4. So this is the unit ramp signal. This is like a ramp signal. Okay. So this is the, for the discrete type of signal, it is represented. This is the graphical representation, and this is the mathematical representation of the unit ramp signal. Now for the like continuous type, we are representing this signal by the small r t. For the continuous type, it is represented by the continuous rt, and this is value is equal to t for t greater than or equal to 0, and its value is the 0 otherwise. Okay, so this is the RT unit ramp signal. Its value is the t for t greater than or equal to 0, or its value is the 0 for the otherwise. So this is the in the continuous type. This is in the continuous type RT. So next we are having like a signal, like here we are having t, here we are having a negative t. So how to represent it is like a representation of this signal is like this one. This is the RT. Okay, and this is the graphical representation of the unit ramp signal. Okay, so it is like a straight line we are representing for the continuous time signal, because in the continuous time signal means we are having values. In the first lecture I have explained continuous time signal, they are having the value at every instant of time. Means for the values like zero point 0.1 seconds, zero point 0.2 seconds, at every seconds they are having their each values. So we are representing it as the linear line basically. So for the discrete time signal, they are having some values at every instant of time. For the particular instant of time in the discrete time, they are having the value 0 at the 0, 1 at the 1. So in between 0 and 1, they are having no value. Means they are having the value at particular instant 0, then 1. Like in the 0 0.1, 0 0.2, 0 0.3, they are having no values. Okay. So this is the discrete type RAM signal. This is the continuous type RAM signal. Okay. So with this next, we are having like a relationship of the like a unit step, unit ramp, and the unit delta function. So like in the examiner mostly ask the, in the objective type question or in the like a theoretical, they will ask the 2 mark question. What is the relationship between the unit ramp signal, unit step signal, and the delta function. Okay. Again, I am explaining you there are the three types of the important standard signals we are using in the signal and system. First one is the unit step signal. Then we are talking about the delta function. And third one is the unit ramp signal that I have explained here. Okay. These three signals are very important. And examiner will ask you a question. What is the relation between these three signals? Means actually we can drive this signal from we can drive this signal unit ramp signal from the unit step signal or from the unit impulse function also. So there is the relationship between these three signals, unit step signal, unit ramp signal, and the delta function. So I will explain you the relationship between the unit step signal, unit ramp signal, and the delta function. Okay. So first of all, we are having three signals. Okay. So we are having a delta t function that is called the delta function, unit impulse function, delta function, unit impulse function. Okay. So we know this delta t is its value is the 1 for is equal to 0. Okay. First we are having delta function, then we are having a ut, that is the unit step signal. Okay. That is the unit step signal. Then we are having a rt. I'm talking in the like a, this is in the continuous time signal. Okay. So this is the unit, this we will write down like a unit step signal. Okay. This is the unit step signal. This is the ramp signal. Okay. So we will find out the relation between these three signal, delta function, unit impulse, step signal, ramp signal. Mostly the examiner asks you what is the relation between a delta function, these three signals, delta function, unit step signal, or the unit ramp signal. Okay. So when I will do the integration of delta function, simply I will explaining you. When I will do the I denoting the integration, I is representing the integration. Okay. When I will do the integration of the delta t, we are getting the unit step signal. Okay. I is representing the integration. When I am doing the integration of the delta t function, we are getting the unit step signal. When I am doing the integration of the ut, unit step signal, then we are getting the unit ramp signal. Okay. So this is I is representing so students, when we do the integration of the delta function, basically when we do the integration of the delta function, we are getting the unit step signal. And when I am doing the integration of this unit step signal, we are getting the ramp signal. Okay. So I is representing the integration. Okay. So we will do the reverse also. Okay. We will if I am taking this rt function. Okay. So we can backtrack this signal also. How we will do the backtrack of this signal. Okay, so if I am writing the first I will write down the unit ramp signal. Okay, RT. If I will do the if I will do differentiation of this signal. Okay, if I will do the differentiation of this RT, then we will getting the UT, unit step signal. When I will differentiate this RT, I am differentiating the ramp signal, I am getting the unit step signal. And when further I will differentiate the like a UT signal, then I am getting the delta T function, unit impulse function. Okay, so likewise I will write down here like a RT is equal to double integration of the delta T. Okay, so like examiner asked you this question, what is the relation between the RT and the delta T? Okay, you can write down like a RT is equal to the double integration of the delta T. Okay, so we can write down it also as the D square by dt square. Double differentiate of the RT is equal to the delta T also. Means when we will double differentiate this RT signal, when I am doing the double differentiate of this ramp signal, we are getting the delta function as the output. Okay, so this is relationship between the this is the relationship between the ramp signal, delta signal, or the unit step signal. Okay, so this is all about the standard signals, and we have discussed the unit step, unit ramp, signum function. The next we will discuss the topic that is the like manipulation of the signals. Okay, so manipulation of the standard signals we are saying, or so next we are having a manipulation of the signal, that is of the three type. Basically we will manipulate the signal, or we will modify the signal according to our need basically. Okay, so that is called the manipulation of the signal. We will do the manipulation of the signal by the three process we are using to manipulate the signals or to modify the signals. Okay, so these three process are the first one is the time shifting operation. Okay, that is the time shifting operation. Okay, so in this like a time shifting operation, we will shift the time basically. Okay, we will perform the operation of the signal on the x-axis, because time, when we are representing the signal, we are representing the time along the x-axis, and this is the y-axis is representing the amplitude. So time shifting operation is basically on this x-axis. This is minus t, this is t. So all the time shifting operation is related to this x-axis. Okay. Second type of manipulation of signals we are doing, that is the time scaling operation. Okay, that is the time scaling operation. Again, we are talking about the time. Okay, time is represented by the this axis, this is the minus t, this is represented by the t. So this is the y-axis is the amplitude. So time scaling operation means either we will compress the time. Okay, we will compress the time, or we will expand the time. Okay, so these two operations are again performed on the x-axis, that is the time scaling operation. Either we will compress the time, or we will expand the time. Okay, this is the second type. Okay, Third type, we are having the amplitude scaling operation. That is the amplitude scaling operation. Okay, so this is the third type. Okay, so this is the time t, this is the minus t. Here we will are having, so this time scaling operation is performed along the y-axis. We will we will perform the operation on the amplitude. Okay, we will do the additions in the amplitude, we will do the subtraction in the amplitude, we will increase the amplitude or decrease the amplitude of the signal. So these two operation, time shifting operation or the time scaling operation, it is along the x-axis. It is performed along the x-axis because it is time shifting is related to the time axis. Time scaling operation is related with the time axis. This third type, that is the amplitude scaling operation, that will be performed along the amplitude. Okay, so these are the operations that are related, that is, these three operations is related to the manipulation of the signals. Means we modified the signal according to our need. Manipulation means we will manipulate the signals, we will change the signals, we are modifying the signals according to our need. So these three operations, time shifting operation, time scaling operation, and the amplitude scaling operations, are the part of the manipulation of the signals. Okay, so next we are having like a next, first we will start with the, that is the time shifting operation. Okay, so first we will start with the time shifting operation. Okay, so in the time shifting operation, we will start the manipulation of the signal by the time shifting operation. So time shifting operation is subdivided into the five parts. Okay, this time shifting operation is divided into five parts. First one, we are having a time delay operation. Okay, second type we are having, that is the time advance operation. Okay, third type we are having a like a folding of the signal. Okay, folding of the signal. Fourth type we are having a delay, folding and delay, folding and delay operation. Fifth type we are having, that is the folding, folding and advance. These five operations come under the time shifting operation, and we will discuss this time shifting operation one by one. First, we will discuss the time delay. What is the time delay actually? Then we will discuss the time advance. How the time advance? We will do the time advance. Third, we will talking about the folding of the signal. It is also called as the mirror image of the signal. Fourth operation is the folding and delay operation, and fifth one is the folding and advance operation. So first we will discuss this under the time shifting operation. First we will discuss the time delay operation. What is the time delay operation basically? So when first we will discuss this time delay. Okay, so what is the time delay basically? So first we will discuss the time delay. What is the delay actually? Delay means when we are sending the signal from the one place to the another place. Okay, we are not getting the signal instantaneously. Okay, there is the some delay in the signal, and that delay is represented by the like in the nanoseconds, it may be in the microseconds. Okay, so with the advancement in the technologies, we have reduced the time delays. Means when we are sending the signal, we are receiving the signal instantaneously, with with less time delay. Okay, so time delay is related with the like a delay in the time, means we are not getting the signal instantaneously, means we are getting the signal after some time period, that is the time delay. Okay, so in the time delay, in the signal and system, we are representing this time delay by the x n minus k, means we are having the x n as the original signal. Okay, we are having this, it is as the original signal x n, and its delay is represented by the d x n minus k is represented the delay of the signal basically. Okay, so delay is represented by the x n minus k. Okay, so likewise, this xn is the original signal and delay is the xn minus k. So if I am taking the signal xn is equal to 1 comma 2 comma 3 comma 4, I am having the signal xn is equal to 1 2 3 4, and this is arrow is representing the position. Okay, so if I am drawing this signal xn signal, okay, if I am drawing this xn signal, graphical representation of this signal is like, here we are having a n, here we are having a minus n, so this is the x n, here we are having the 0 1 2 3. So hello. So so this xn is equal to 1 2 3 4. Okay, so like we are having this xn is equal to one signal x 1 2 3 4. Okay, so if I am graphically representation this signal, this is represented by the n 0 1 2 3. Okay, so at the n is equal to 0 we are having a magnitude 1, at the 1 we are having a magnitude 2, at the 2 we are having a magnitude 3, at the 3 its magnitude is the 4. So this is my xn signal. Okay, so this is the 1 2 3 4 magnitude, and this arrow is representing the n is equal to 0. Okay, this is clear to everyone? Hello.
Yes, sir.
Okay, so like this is the xn signal. Xn signal is represented by this graphical representation. Now I want to delay this signal by the one sample. Okay, so here we are representing the delay by the xn minus k. Okay, so there is the k value is the 1, I have taken xn minus 1. Okay, so delay means how we will delay the this signal xn minus k1 when we are performing the delay operation. So we will shift the signal toward the right side. Okay, this is the shifting toward the right side. Okay, so whenever you have to perform the delay is represented by the negative sign, and it is shifting toward the signal toward the right side. Okay, how much sample we will shift the signal toward the right side, that is equal to the one sample. So I am shifting this signal toward the right side, means the sample which is present at the n is equal to 0, it is moving toward the n is equal to 1. The value at the 1 it is moving toward the 2, two's value to the 3, 3 values toward the 4, means we will shift one sample toward the right side. Okay, so if I am drawing this signal again, okay, so this is the n and this is the minus n. Okay, so this is the x n minus 1. Okay, so if I am drawing this delay signal, graphical representation of this delay signal, so the value at the 0, here we are writing 2 3 4. Okay, so value of the 0 is shifted toward the 1. The value of the 0 is the 1, it is moving toward the 1. So here I will write down the value is the 1. Okay, zero's value shifted toward the 1, means shifting the signal toward the right side by one sample. So it is value is the 1. Add the 2, its magnitude is the 2. Okay, add the 3, its magnitude is the 3. Add the 4, its magnitude is the 4. 5, we are having a 0. This is the delay of the one signal, means we shift this signal toward the right side by the 1. So delay is represented by the negative sign. Okay, so this is the original signal. Okay, delay is represented by the, here I am representing the one sample delay. Okay, so one sample delay means shifting the signal toward the right side by the one sample. So magnitude, here we are having a magnitude 1. At n is equal to 0, magnitude is the 1. So this is shifted toward the 1. One sample move toward the second, second toward third, third toward the fourth. So this is the shifting of the signal toward the right side. Okay, so how to represent this x n minus 1 signal mathematically? So at n is equal to 0, we are having a magnitude 0. Okay, this arrow is representing n is equal to 0 magnitude. So here we are having a 0 magnitude here, because 0 samples move toward the one side. So then we are having comma 1 2 3 and 4. Okay, so we are having x n minus 1 sample is equal to 0 1 2 3 4. So if I am adding these 0 to represent this signal, if I am adding the 0 at the starting point, this process is called as the zero padding. Zero padding is what is called the zero padding. Zero padding is the process when we are adding 0 in front of the signals, okay, at the starting of the signals to represent the signal. That is called the zero padding. So this is about the time delay. Time delay means when we are sending the signal, we are not getting the signal instantaneously. Okay, we are getting the signal after some time period. That time period is representing the delay. So whenever you are communicating in the foreign countries, like in the Canada or Australia, you are getting some delay of the signal. Means you are not like received the like a voice of the receiver instantaneously. There is some delay. That is called the time delay. But in the signal and system, in our mathematical representation, we will represent the delay by the x n minus k. Okay, this negative sign is representing the delay of the signal. So I have taken the one example. X n is the signal 1 2 3 4 is my original signal. I will I will draw this signal as the xn. 0 amplitude is the 1, at the 1 amplitude is the 2 3 4. This is the xn signal. Okay, so if I will do the delay of this signal, means delay of the one sample, so I will move this signal. When I am delaying the signal in the signal and system, I will move this signal toward the right side. Okay, I am moving this signal toward the right side by the one sample, because here I am taking the delay of the one sample. Okay, so I move toward this signal toward the right side by one sample. So this is how I represent this signal graphically, and mathematically I represent this signal. When I am adding the 0 at the starting of the signal to represent that signal, that process is called as the zero padding phenomenon. Okay, so this is all about the time delay operation. Okay, so next type we are having, that is the time advance. Okay, so this is the first type, that is the time delay. Second type we are having, that is the time advance. Okay, So what is the time advance operation? Okay, so like a time advance means I am not started the system, but I am getting the output. That is called the time advance. Means I have not started my system, I have not on my system, but I am getting some output. That is called the advance. Before the signal I am applying, we are getting this signal as the advanced signal. Okay, so in the real life, in our real life, we are not having the time advance signal. Okay, we are not having the any examples of the time advance signal. Okay, so time advance is possible only when I am stored the signal in the memory of the computer. Okay, then there is a possibility that we are getting this time advance signal. Okay, so what is the time advance operation? Here we are having, if we are having a xn as the original signal, then with the plus sign, here we are having xn plus k, that is the signal advance operation. Okay, so again I am taking the same signal xn as my original signal. This xn is having the 1 2 3 4 amplitude, and it is graphical representation by this signal xn. Then it's time advance of the one sample. Okay, now I am talking about the advance. Okay, advance of the one sample, because I have taken xn plus 1. Okay, this means time advance. Okay, advance of one sample. Okay, I have taken. So when we are talking about the advance of the signal, we have put the positive sign, plus sign is there. Second thing, how to shift the signal. For the time advance, we are shifting the signal toward the left side. Okay, for the, again I am repeating, when you are performing the advance operation, you are shifting the signal toward the left side. Okay, in the case of the delay, we have shifted the signal toward the right side, but in the case of advance, this is the shifting of the signal toward the left side. Okay, so how to represent this x n plus k? Okay, how to represent this x n plus k? I will draw this signal again. Means we have to perform the advance operation. Advance means shifting toward the left side. This is my original signal. Shifting this signal of one sample toward the right side, right, sorry, left side. Shifting of the signal toward the left side, basically. Okay, so this is my original signal. Zero amplitude is the one. If I do the shifting toward the left side, okay, means zero sample move toward the minus one. Okay, left side means they are moving toward the minus one. Zero magnitude is moving toward the minus one. One is moving toward the zero position. Two is moving toward the one, and three is moving toward the two. Okay, so this is called the time advance shifting of one sample toward the left side, because here I am using x n plus 1, only one sample advance. Okay, so I am writing this is the n, this is the minus n, this is the x n plus 1. Okay, so here we are having minus 1 0 1 2 3. Okay, so 0 magnitude we are having a 1. At the 0 n is equal to 0, we are having a amplitude 1. Okay, this we have to move toward the minus 1. So at the minus 1 we are having the 1. Now 1, at the 1 we are having amplitude 2. This is moving toward the 0. So here we are having a 2. At the 1 we are having a 3. At the 2 we are having a like a 4. At the 3 we are having a 0. So this is the time advance. We shifted the signal toward the left side shifting by one sample. So how to represent x n plus 1? This is by the, we are having a 1 comma 2 comma 3 comma 4, and at the n is equal to 0 we are having a magnitude 2. So arrow is representing the magnitude at the n is equal to 0. Okay, this is the time advance operation. Time advance is represented by the positive sign. Okay, here we are represented by plus sign. Next thing, advance operation is related with the moving the signal toward the left side. Okay, so this is the time advance. We move the signal toward the left side by number of samples. Here I am using a is equal to 1. You are having a values like a is equal to 2, a is equal to 3. Then you will move that sample toward the left side. So this is the time advance operation. Okay, so this is the second type. First we have done the time delay. Second type, this is the time advance. Next we are having a like a time folding, then folding and delay operation, folding and advance operation, that we will discuss in the next lecture. Okay,